This video will introduce a cognitive radio algorithm development testbed using Agilent SystemVue simulator and the N6841 RF sensor. In this video, we'll show a live demo of the new cognitive radio development testbed. But first, let's review some concepts of cognitive radio. Cognitive radio is a promising new technology for increasing spectrum utilization. The degree to which cognitive radio fulfills this promise will largely be determined by the performance of spectrum sensing and the cognitive engine functions in the radio system. Now, designers of cognitive radios, which access spectrum on a secondary basis, are faced with the daunting challenge of designing for a dynamic spectral environment that is largely unknown and uncontrolled. The cognitive radio testbed introduced in this video addresses this design challenge with an innovative combination of remote spectrum sensing, simulation, and RF test equipment. This development testbed can help you accelerate your whitespace algorithm development activities and to minimize risk by developing and testing algorithms using real-world spectral environments. The key functional blocks of a cognitive radio are shown in Figure 1. The radio policy can be described as a set of rules which provides operational boundaries and limitations. The actual operating characteristics of the radio are determined by the behavior and control block using information from the other functional blocks. As an example, the behavior and control block can select a modulation and a frequency based on what's allowed by the policy using spectrum resources deemed as available by both the spectrum sensing and database blocks. One motivation for cognitive radios is increased spectrum utilization in situations where it's not practical to have a centralized and all-knowing spectrum resource manager. In these situations, cognitive radios determine what spectrum resources are available and how best to use them. This process is sometimes referred to as filling the white space, as depicted in Figure 2. Here, one of the whitespace radios appears to simply change frequencies. The other radio, however, seems to anticipate the behavior of the protected signals and completely modifies its signal spectral shape to avoid interference while filling the new spectrum holes. Orthogonal frequency division multiplexing, or OFDM, techniques are particularly well suited to cognitive radio applications because of the ease with which signals can be adapted to channel conditions and capacity requirements. Cognitive radio development presents a number of significant challenges and barriers. For example, real-world spectral environments need to be used for algorithm development and testing. However, the use of live signals creates test conditions that cannot easily be replicated from one day to the next. Laboratory and R&D environments provide design tools and the equipment to develop and test algorithms, but emulating real-world cognitive radio spectral environments to adequately design and test algorithms can be very difficult. Metrology-grade test equipment is needed to test radio algorithms, but off-the-shelf test equipment typically does not support signal types that represent the realistic cognitive radio environments that radio would be exposed to. To address these challenges, a new cognitive radio R&D testbed combines remote field sensing with a toolset-rich controlled lab environment. This allows algorithms to be developed and tested with real-world cognitive radio environment signals. The remote field portion of the R&D testbed consists of one or more N6841 RF sensors located at various geographic locations. The sensor locations are selected to gather data from different environments or to test cooperative sensing algorithms within an environment. The lab portion of the R&D testbed utilizes Agilent SystemVue simulator to capture the cognitive radio environment data from the remote RF sensors. Once that data is brought into SystemVue, SystemVue's math language and math language debugger can be used to write and test cognitive radio whitespace algorithms with the remote field captured signals. The OFDMA simulation modeling capability in SystemVue can then be used to configure and evaluate OFDMA mobile WiMAX and LTE link performance. It can also be useful to download and store remote field sensor data to test equipment for hardware DUT testing in the lab environment. Simulation provides the link between the remotely located RF sensors and test equipment in the lab. The captured field sensor data can be downloaded to signal generator arbitrary waveform generators to recreate the field captured signal in the lab environment for DUT testing. Now let's take a look at a mobile WiMAX cognitive radio example which will be demoed live in this video. The flow involves capturing a cognitive radio spectral environment from a remote field location. The sensor is located in western Washington State, while the simulation and test equipment are located in an office environment in eastern Washington State. SystemVue's math algorithm processes the captured cognitive radio spectral environment to determine potential white space. The potential white space frequencies are evaluated against a policy to determine valid white space frequencies and available bandwidth to support an OFDMA mobile WiMAX link. The math language algorithm then configures and scales a mobile WiMAX center frequency and channel bandwidth to either 5 MHz or 10 MHz, depending on the available white space it sensed and calculated. It's important to note that we're using WiMAX and LTE as example signals. A user would probably replace these with their own radio designs. In addition, we're using a single sensor, a fairly simplistic spectrum sensing and cognition engine, and you would replace these with your own algorithms, which are likely to be much more sophisticated. The coded bit rate of the configured mobile WiMAX radio link is evaluated to determine radio link performance. The captured cognitive radio environment is also downloaded to test equipment, a signal generator arbitrary waveform generator, to recreate and analyze the cognitive radio environment. Lastly, the cognitive radio spectrum is demodulated both in simulation as well as test equipment using Agilent's 89601 vector signal analyzer software. Now let's view a live demo.